be 2 handouts going around, and excuse me, for the homework assignment, if you have it in a hard copy, please pass it to the forward somewhere this way. You can either turn it hard copy or turn it in online. Either is fine. If you're using funny formats or documents that need special, stuff to read the documents, it's probably better to print it. So it's not turning, it's fine. And you should have 2 handouts passing around. One is the class lecture, and one is the solutions to the first homework assignment. Okay, we can get started. Good morning. I noticed that people have started work on the homework project, and I guess a lot of people are running into all kind of problems, right? In terms of kernel panics and stuff. And I'm guessing the different panics are for different reasons for different people, right? So when the kernel panics, whatever the error message it gives you a little hint on where you should proceed. Because when I tried 2.6.14, it compiled with no problem at all. And I guess some of you got the one message said, if they said enforcing to 0, then it went through, right? And the real reason is the kernel that you configured tries to be secure, so it's trying to enforce policies, and it couldn't find the policy, so it bombed out, right? So did anyone else have success in going past the? How many of you got panics?
I have panic, but it's set enforcing to 0 too, and it's still panicked on me.
Yeah, because you probably have different issue which is causing your panic.
Ours is panicking also.
I'm sorry?
Ours is panicking also.
Do you know for the same thing?
Huh?
Do you know for the same kind of stuff or different thing?
I haven't tried that, but I don't know. I was getting a different error.
Okay. Yeah, the error it gives before it fails is probably a good place to start, right? So look for it, and I think usually if you get that error message and give it to Google, you probably find what you should do. If you're still running into trouble, talk to me or the TA, right? So, and you should have the homework assignment solutions. We'll have the exams on Friday, right? So today we'll continue on with the more algorithms on how to do CPU scheduling. So far last week we looked at processes and threads, and we're trying to see how the kernel would assign the CPU to a process or a thread, right? So is the notion of threads and processes clear so far? Right. So we can move on to the scheduling, how exactly you would do that. And in essence, if you want to do multi-programming, right, the idea is if you have idle cycles, idle times when the process which is running is doing I/O or something and it's not doing something, right? Multi-programming basically tries to give that process to give the CPU to another process, so hopefully that you can keep the CPU busy, right? And you can only do that if you have many processes to run, and so once you have that ability, the CPU, the OS has to figure out which process to run, and that's the process of scheduling, right? And for that to work, you need certain conditions. So people, before you develop these algorithms, look at the system. So there's a big part of operating system research is trying to figure out what people do with typical operating system, what people do, what kind of things that they do, and trying to use that to make a better system, right? So one of the things you need to do for scheduling is you need processes to go through these phases. Either use the CPU and give up the CPU and go through some I/O. Because if the process never does that, if no process ever does I/O, then there's no point in doing scheduling, right? Because all your processes want CPU all the time, so you have to let them go, let them wait till they finish, and so on, right? So what you're looking for is some sort of a behavior, and obviously this is the observed behavior too, which is the processes would have to do some kind of a useful work using the CPU, and then they go off and do I/O, and when they're doing I/O, they don't need the CPU, right? So they have to go through this kind of a CPU I/O cycle, read something, do some processing, read something, do some processing, and so on. And most programs exhibit this behavior. That means you need to do. So there's a possibility of doing CPU scheduling to get more throughput out of the system. So whenever there's I/O, you could use that for something else. And the other stuff that the OS developers do is trying to figure out what these numbers are. What is the typical time? How long do these bursts last? And this is one figure that is in your book. Obviously, it depends on what kind of applications you have. So companies like Microsoft spend a lot of money trying to figure out what this graph looks like. How much time is spent in CPU cycles? How much time is spent in I/O? Because that defines how well they can define the scheduler to match what you notice here, right? To get better throughput, right? So some people do this research, and typically you see this stuff. You see a lot of CPU bursts are very short. So if you look in the graph, the burst duration is on the x-axis, and the y-axis is the frequency, right? So you notice a lot of the CPU bursts are very small. There are a few which are very long, right? So most tasks, you expect them to use a little bit of CPU, get what they have to do, and then relinquish the CPU, right? Which means that you can actually run a lot of processes because you can let one go for a little bit, it's done, then you can run the other one, right? So exactly why you would look at these things. If the graph was different, if the graph was showing that all the CPU tasks are long bursts, that means you can't really do the kind of stuff that you would want to do, right? So essentially, the CPU scheduler. Remember the state diagram we had before about processes. The processes go through ready state, and then they're running. They go through I/O waits and stuff. So the scheduler basically has opportunity to schedule a new CPU at any of these points which is listed here. One is if a process. The last point is that when the process terminates. If another process terminates, then the CPU allocated to that process is free to be given to somebody else. The other ones are if a process waits for I/O, right? If a process wants a new I/O, then that's a good time to take the CPU from that process and give it to somebody else. If I/O finishes for a process, right, then that's a good time to decide if this process should get to run or it should be put in the ready queue, right? So if I/O finishes, then potentially you can take the CPU from somebody who's running and give it to the process whose I/O just finished, right? Or the other reason is the CPU is the process is using too much CPU, so the kernel can take the CPU away from you and give it to somebody else. So these are times where the OS gets to decide what it should do, right? And some of them are what is called non-preemptive, and some of them are preemptive. Non-preemptive is cooperative, which basically says that the process has nothing else to do, so it's a logical point for it to give up its CPU. So for example, if the process terminates, right, then that's a good point for it to give up its CPU and schedule something else. And same for when it asks for I/O. When it asks for I/O, the application stops and it makes a conscious effort to make this I/O, so it's a good time to take it. Whereas the other two, right, where the process is running and it's using too much CPU and the OS decides to take it away, right? And the case where some other process I/O finished and it wants a CPU, so it's trying to boot who is running on the process right now, are called preemptive. basically the process which is the victim never asked to be taken off. So, which means that it never prepared for it, which means that it doesn't actually know what's going to happen. So it probably never left all the things in good state for it to come back, right? So if it's using some data structure that somebody else may look at, it may be in an inconsistent state, right? At the least, it may be making a system call inside the kernel, doing something inside the kernel on its behalf. If you just yank it right there, the kernel may be in an inconsistent state because the kernel is trying to do something. So you have to make sure that these stuffs are dealt with, right? Usual thing you do is you make the kernel processes non-preemptive. So whenever a process is inside the kernel doing something, the OS will wait for it to finish before it lets it go. But you have to make sure that either from the kernel side or from the application side, you are aware and you deal with this, right? From the user side, that's what we'll see in the next module. You have to make sure that you lock and stuff. But from the kernel side, you would typically not let kernel processes be interrupted. So you disable all interrupts. So when you go into the kernel, you get to run, and usually that's okay because the kernel, you're not supposed to do too much stuff inside the kernel anyway. And once you're done, then you make a decision on which processes to run. Right? So that's the two things. So the older operating systems like your Windows 3.1, old Mac and everything, would do the non-preemptive or the cooperative scheduling. Right? It makes the stuff easier. It makes the writing the kernel easier. It makes the writing the applications easier. But if any of you have used some of the older operating systems, you would know that if a process was holding on to a CPU, so the two reasons why you want to preempt is when you're using too much CPU and I want to get it back, right? If you're using non-preemptive scheduling, and if a process is using too much CPU than it should be using, right, then you have to basically wait till it relinquishes, right? So if you have a hung process, then there's nothing you can do. You can't. The OS cannot come in and take the CPU away from it, right? So some of your older operating systems would have noticed that one hanging process would make the whole system hang, right? Modern operating systems like Windows XP or Mac or something won't have that problem. Even if one process is hanging and doing stuff which it didn't intend to do, right? The kernel can still preempt, can still take the CPU away from you. So even though the process is going in a loop asking for the CPU, it does not get all the stuff, right? And the actual function which does this switching is the dispatcher. So there's inside the kernel there's a dispatcher routine which figures out. So once the scheduler figures out that some process is the victim, right? It does the switch the context. It basically stores all the local data about that particular process, and bring the new process in. So restore all the context from the process which is being woken up, right? Switch to the user mode because all this is running in the operating system in the kernel mode. Become a normal user and start running from where they left off. So for the most part, it's transparent to the user, except these things take time, right? So you want this stuff to happen as quickly as possible because this is all overhead. This is all stuff that is being done by the operating system. This is not useful work. So you want this to be as quickly as possible. And the smaller it is, you can do the switching a lot more. If it takes you a lot of time to switch each process, then you want to let it run for a long time. So you try really hard to make these things as small as possible. And usually they are. It takes like a few microseconds to switch a process on most modern machines. So the real aspects of scheduling, CPU scheduling, is what metric do you use to optimize the system, right? So you have multiple processes. The OS has multiple processes, which are all simultaneously running. So it gets to choose which ones to run next and which ones to run later, right? And depending on what it's trying to do, what it's trying to optimize, you may see different performances. So for example, these are the common metrics. The first one is CPU utilization. Right? CPU utilization says how much of the CPU is actually used for useful tasks, and you want to keep it as a maximum, right? You want to increase that, which basically means the CPU is doing useful work all the time, right? And the other metric is throughput. The throughput says how many processes are completing in a given amount of time, right? And you want to again maximize throughput, right? And I'll first go through all four of them and tell you what's the intricacies of each of those, right? The other one is it's turnaround time. It basically says, when the task comes into the system and it how long does it take to get out of the system? You want that to be minimal. You want that to be no more than the execution time of the process. You don't want it to wait on any queue on the system. And the waiting time basically captures how much time it was on the ready queue on the CPU scheduler. And response time says how much time. So when you start a process, how long does it take before you see a response on your screen? So some of these goals they conflict with each other, right? To improve the CPU utilization, you don't want to switch process. So CPU utilization takes into account the dispatch overhead. So if you want to optimize CPU utilization, you want to run the process which you don't want to take the CPU from any process. You want to let it run all the time. If you do that, then your response time and your waiting time would be bad, right? Which means that the other processes will have to wait for a longer period of time. If you want to optimize for throughput, right? Throughput says how many processes you can get through in a given amount of time. So if you imagine a mixture of small and large processes, right? Some which need like 1 second, some which need 10 seconds. Depending on how you mix them, you can have better throughput or worse throughput. So if I look for the next 10 minutes, right, and I have 10 small and 10 large, right, and some of the processes take 1, some of them take 10 minutes. So if I run the longer 10-minute process, I get to do 1 process in 10 minutes. If I do the shorter ones, I get to do 10 in 10 minutes, right? So if I want to optimize for throughput, I would want the smaller processes, which means the longer processes just keep waiting. So their waiting time, turnaround time, and all goes up, right? So you can't really optimize for all of them together. You can't have good utilization, good throughput, and all this stuff. So the key is to trying to find a mix, which works for you, and that's where all the operating system developers spend all the time. They're trying to find a mix which will give you a good mixture of whatever you're trying to achieve, right? For whatever type of things that you see people are doing. So if you're developing Windows XP for desktop, right? Then somebody decides that it should have, you should place 80% importance on the response time and 10% on CPU utilization or what have you. You find what the mix is, you find what typical users are trying to do, and you try to see what this policy would do to that user if it will make them happy, right? And if you believe that whatever your policy would make that particular person happy, then you are a successful operating system, right? And if you take that particular operating system and try to do something else, you'll notice that it won't do a good job, right? So your servers and stuff are tuned for different stuff than your desktops, right? So we'll go through a number of classical scheduling algorithms before we look at how they kind of mix it up into multi-level stuff for in real operating systems. The first one, the first one is first come, first serve. The idea is whichever process comes first gets to run, and you don't typically preempt these processes. So whichever comes first gets to finish its task and then move on to the next one. Then you can think of shortest job first, practice scheduling, and round robin. And over the next few slides, we'll go through detail of each one of those. Right. The first come first serve. It's a fairly simple scheduling algorithm. Right. So suppose you assume that you have 3 processors and each one wants a CPU time of like 24, 3, and 3. right? Where we don't define what those units are. And you want to schedule them on a first come first serve basis, right? So you can show them in a Gantt chart. Gantt chart basically states that what process is running at what time and what time they finish, right? So it's a graphical representation of how that processes would be scheduled. And so if they came in that order, P1, P2, and P3, so P1 gets to run for 24 seconds, and at 24 time unit, P2 starts, runs for 3, and then P3 starts and runs for 3, right? So if you look at the waiting time for P1, it's 0, waiting time for P2 is 24, P3 is 27. So the average waiting time is, if you do the math, it's 17, right? But it depends on exactly what order it reaches the system. So if you change that order to P2, P3, and P1, right, where the smaller jobs came in before the larger ones, now the average waiting time goes to 3. Right? So basically the P2 gets to run immediately, P3 gets to run after 3 time units. P1 waits for a little bit longer, but not as long as the other one. So depending on, this is probably better than the other one, depending on what trend to optimize. And this effect is called the convoy effect. This is sort of what you see on a highway where you see somebody going at 40 miles an hour on a single lane, and there's a whole bunch of cars behind it, right? So as long as the one in the front does not clear out, you tend to accumulate a lot of processes behind it. So it's better to have the faster cars in the front, or better to have the smaller processes in the front. But it depends on how these things span out, right? Another variation of this is trying to find out the shortest job and let it run first, because that's what we saw in the first come first serve. The shortest job will tend to enter the system and leave the system sooner, so you can move the longer jobs later on, right? And so you figure out what's the shortest. You figure out the CPU times of all the processes and figure out what's the shortest one of them and let them run, right? You can have two variations. One is preemptive, one is non-preemptive, right? Even though we can say that in a theoretical fashion, if you figure out what the CPU time and all those things, in reality, you don't actually know that. In reality, it depends on what this program is running, say. So you're trying to predict what the future is. So you're trying to predict what the future CPU requirement of these tasks are, because the scheduler is running now, right? The scheduler sees 3 processes, right? It does not know what process would need how much CPU on the next cycle, right? So all it knows is the history, right? So it'll use the history to figure out how these things work. But for now, assume that you have, the oracle, and you know how much CPU each of these processes would require, right? If you're talking about a non-preemptive, then you figure out at that instant which one has the lowest requirement in the future and let that run, right? If a new shorter process comes in, it has to wait. Whereas if you do a preemptive, right, whenever a new job comes into the system, new process comes in, then you decide to see how much time is left for each of the processes and schedule the shortest of them, right? So if a process was running for a while, then it would have, it doesn't need as much CPU, so it keeps changing. I have graphs in the next few slides to show how these things work. You can prove that shortest job first is optimal for the, because it gives the minimum average waiting time, right? So I'm not sure if you've taken algorithms course yet. That's in the senior year, right? So you will go throh big O(n) and other complexity measures to figure out what optimality means, right? For now, assume that it's the optimal algorithm. It's the best algorithm you can think of to optimize for minimum average time. The only caveat is you don't know the future. So if you knew what the future is, if you knew what the future scheduling time of request time of each process is, then shortest job first would optimize for the minimum average waiting time, right? you try to optimize these, and so here are some of the more graphical examples of how these things work. So the first is the non-preemptive shortest job first, right? So you have 4 processes over there, process 1, 2, 3, and 4. And then they have their own arrival times. You know, they arrive at 0, 2, 4, and 5, and they have different burst times. So the process 1 comes in at time 0.0, and it requires a burst time of 7, right? The scheduler at that time has only one option. It only has one process, so that's the shortest job, so it gets to run. So if you look at the Gantt chart at the, over there, it's not preemptive. So once you schedule, it does not give up its CPU. So the P1 starts and it runs up to time 7, right? And at time 7, all the other processes would have arrived, right? Because P2 came in at 2, P3 came in at 4, P5 came in at 5, right? So at time 7, all 3 of them are waiting, all 3 of them can go. So you choose the shortest jobs among them. And the shortest among them is P3, so it gets to run, right? And then P2 and P4 require the same amount of time, so you can choose either one of those. You choose 2 because it came the earliest. So you would schedule these tasks in that fashion, right? And it has a average waiting time of, if you do the math, of 4. So since you have no way of preempting, P1 cannot be preempted even though it has the longest waiting time. Just because it came first, it gets to run, right? So if you change that to a preemptive version, right? So now it gets a little bit more complicated because the P1 again gets to run because it's the shortest path when it first came in. It gets to run till 2, right? When process 2 comes in, and process 2 needs 4, whereas process 1 would only require 5 at that point. It needed 7 to begin with, but now it only needs 5. So P2 gets to run, right? And at 4, P3 comes, P3 requires only 1, and so on, right? So you work through the stuff, and the average waiting time for this particular schedule happens to be 3. So you add up the waiting time of the different processes. The average tends to be 3, right? So depending on what the mixture is and what you're trying to do, you tend to see different behavior, right? So like I said, the real key is trying to figure out what the next CPU burst is, and you actually can't know that, right? So all you know is the past. So you can keep a history of what the processes have been doing and trying to figure out what the future should look like, right? And there's a lot of equations, there are a lot of ways of doing this. Basically you're doing exponential decays, right? From your math classes, you're trying to do an exponential decay where you're trying to see how much effect the history should have on the future, right? So the exponential decay function is the equation on point 4, right? It basically, so where the alpha defines how much of history you want to take into consideration. If alpha is 0, you don't look at history. If alpha is 1, all you look at is history, right? And you want to have a mixture of these things, right? So the specific equation is not that important. The idea is you want to try to predict what the future is based on the past, and how well you do that depends on how well you want the history to predict the future, right? There are a number of reasons why history is a good indicator, and a number of reasons why history is not a good indicator, right? If a process is doing a loop, right? If it's going through a loop and doing the same thing over and over again, then in that phase, history tends to be a good indicator because whatever it did before, it keeps doing. So if you're going through a loop 1,000 times, whatever you did in the loop 1 is probably what you're going to do in loop 2, loop 3, loop 4, so on, right? And if a process is not going through a loop, if it's going through a straight line code, then history is not a good indicator of what the future is, right? So depending on what the developers think that the operating system is going to do, they can use the alpha, choose these parameters so that they can figure out how much history should affect the future, right? And so this is the graph in your book trying to show how a CPU burst would affect what the prediction would be. So if you plug it into the function we had before, and if you notice a certain burst history, right, the blue line is the one that you would guess, and again, you want to make sure that the future predictions are as close to what they were, and again it depends on what the application is actually doing, which you can't really predict, right? So the OS is trying to do a good job of trying to predict what the application would do without knowing anything about the application at all, without knowing whether the application is going through a loop or if it's going through a straight line code. So it's trying to figure out what it is. In some cases it works good, some cases it doesn't work so good, right? So in the function that we used, if you use the alpha as 0, history does not count at all because the prediction for the future, tau of n plus 1 basically becomes the prediction for the past. So whatever you matched in the past is what you predict for the future. Whereas if you have the alpha equals 1, only the history counts, right? And different values will tell you how far back in the history you should look at. The other problem with maintaining all this stuff is the OS has to maintain all this stuff. So OS has to maintain how much of the CPU you used in the previous running times, right? So if I want to look back in the history for the last 10 runs, which means that I have to have a circular kind of list somewhere where I keep track of all this, all the times that so when I gave the CPU, how much of it did you actually use? I'm going to put that into this table, right? The longer the table is, the more I have to maintain. Remember, all this is happening when a process is being switched, right? All this is overhead. So you have to balance with that too. So you're doing a short-term scheduling, so you're not trying to be as optimal as possible. So if your work shows that you can do a good job if you went for a history of 20, right? You have to balance that with the fact that going through 20 may mean that you need 100 bytes of memory, and it slows down your scheduling by X amount, which adds to your overhead and stuff. So you have to balance that to see how much history you want to look at, right? So usually you don't look at too much of history because, like I said, since it's not even expected to be accurate, so you want to find a good mixture, right? And that depends on the particular operating system, right? So those two algorithms, the first come first serve is simple. That's all you can say about it, right? It suffers from the convoy effect because depending on your luck, a long process upfront can delay all the processes which come after that. Whereas a shortest job first, depending on whether you're doing preemptive or non-preemptive, can do a better job, right? If you can predict what the future is, right? So essentially what we are trying to come up here is the first come first serve it's fair in some sense. It depends on whatever order it comes in, the OS decides what should run. But a more realistic algorithm, thank you, would give priority to certain processes. It wants to choose certain processes over certain other processes, right? For some reason it decides that even though they came in a certain order, letting one process go first would solve its goal, be it throughput or waiting time or whatever, right? And again, you can have the same notion of the preemptive or non-preemptive, but here, all things being equal, the OS gets to decide what should run next, right? And in effect, the shortest job first is a priority-based scheme because it decides that your CPU for the future, your CPU burst for the future gets to decide what your priority is, right? And there are a number of variants of this. You can decide based on how big the process is and a whole bunch of stuff. And that's general class of priority-based scheduling. So the idea here is somehow it decides that one process has more priority than the other one. And how it does that depends on a particular operating system. But once it decides that, it depending on whether it's preemptive or non-preemptive, you can take the CPU and give it to the higher priority task, or let them finish if it's non-preemptive. And the general problem with the priority-based schemes are lower priority schemes tend to starve. Basically, they don't get to run at all, right? So if you have the lowest priority in the world, you only get to run when no one else wants the CPU, right? And I think your book has an anecdote that, one of the old mainframes, when they shut it off, they still found an old priority task from the day it started. After 6 or 7 years, it's still waiting in the queue, right? And that's what will happen, right? If you're the lowest priority and you don't get to do anything, then you starve. Typical operations, yeah.
For preemptive shortest job first, we run a similar problem there, because if there's just there are some threads that take an incredibly long amount of time prediction-wise, they might never
Yes.
get executed because they
Yes. That's an excellent point. So if you go back to the shortest job first, and if you're doing the preemptive, right? And so basically you're giving highest priority to smaller times. So if you need a large chunk of time, right, then you have the lowest priority. So you never would get to run, depending on the mix, right? In general, most of the scheduling would perform poorly if you don't have any CPU at all, right? So even in that case, right? So most scheduling algorithms do not like the load to be too high. I'll give a number. I think that your book gives 80 or some odd number, right? So the idea is if you have 1,000 processes to run, right, and they all require equivalent of 1,000 CPU hours, right? And you're trying to schedule them on one CPU. There's not a whole lot you can do, right? So even in the case that you talked about, if one process needs 1,000 seconds, right, and you keep constantly getting some processes which need 1 second, right, which means that the 1,000 will always starve because you always have constant supply of the other ones, right? And that is called the system is heavily loaded. The system is so loaded that it can't possibly solve all the stuff. Yes, if you do some different priority, then it gets to kind of limp around, but it's a sign of a different problem. But yes, because short job is in fact a priority-based scheduling, right? And you do get starvation, and sometimes it's okay. Sometimes the starvation is not a bad thing, but sometimes you want to deal with that, right? So, for example, in most of your machines, if you notice, if you look at the processors, if you look at the tasks or whatever, depending on your operating system, right, you'll see there are some processes in the background scrubbing stuff, some processes which are cleaning stuff, some processes which are doing backups, or some what in Unix is called daemons, right? They're running in the background. They tend to run with a very low priority, right? So I'm guessing most of you work on Windows on a day-to-day basis. Is that true? How many of you don't use Windows? And what do you use? Linux.
OS-10.
Okay.
Yeah, same.
Okay, so Unix kind of stuff, right? So if you run top or PS for the Unix variants, you'll see the process priority, right? So if you're running Windows, right, you can go to the task manager, which shows the processes priority and stuff, right? Which you can actually try here. So if you do a Control-Alt-Del, it should bring up this task manager. So you can basically select what gets to be shown on the screen, right? So right now, all these processes are running on the system, right? And so over on this column, you have the base priority, and you can go through the different parameters to see what priority it's running and all those things, right? And you'll notice that, I hope you notice, there's this process, this idle process, which has no priority at all. So it gets to run when there's nothing to schedule, and this is about, okay. So all the processes are running at normal or high or above normal priority levels, right? So usually you have, so many of these processes I don't recognize what they are. Like there's a AFS creds, which I'm guessing it's doing some AFS credential stuff in the background, right? And some of them I don't really care whether they are high priority or not, right? The PowerPoint, I would like it to be higher priority when I'm actually showing this thing, but there are all these other things running in the background, right? And I'm perfectly happy for some of them to starve, because by nature, I want this machine to do PowerPoint and nothing else when I'm doing the PowerPoint. So if the background backup process or some of this stuff is running at a lower priority and starving, that's perfectly fine, right? I don't want my process, the one in the foreground, which is showing the PowerPoints, to starve, but sometimes it's okay to let some of these things starve. You actually do it on purpose in the priority-based systems, where you say, continuously try to back up the system, right? But I give you very low priority. So you don't actually get to interfere with anybody else. You only get to run when nobody else is doing anything. And of course, you have to do something so that you want the backups to happen at some point, so you don't want it to completely starve, right? And one of the ways you give some level of fighting chance is to aging. So if you're a low priority, but you don't get to run at all, then the CPU automatically bumps your priority. So it keeps track of what your priority that you wanted and what real priority it has. So if you've been very patient for a long time, it keeps bumping you up and eventually lets you run for a little bit, right? And which may or may not be a good thing depending on what you're trying to do. But usually you do that because otherwise you will starve, right? So the next variant is the round robin. Round robin now. So when you talk about round robin, it's the same as the stuff we talked about, except now we have preemptive scheduling, and we give each process, each scheduling a quanta, right? Before we said whatever time you want to run, we let you run. Now we're defining a notion of a quanta and let processes run up to that quanta. So if I decide that each process will run for, say, 10 milliseconds, right? All that it says is every process when it comes in, if I put them in a queue, right, I let each process run for the quanta that I specified, like 10 milliseconds or something. And at the end, I put them back on the queue and choose the next one. So I'm doing in a round robin. I'm going with the first, second, third, fourth, and then coming back to first, right? And each time I only give it that fixed time. I'm not giving it what you asked for. I'm not giving it what your future requirements is. I'm giving you this chunk that I think would be fair, right? So in effect, I'm trying to get rid of this prediction business. I'm not trying to predict anymore. Everybody's equal, right? But everybody gets this little chunk of space, and then I have to preempt you, because if I don't do preemption, this becomes first come first serve, right? First come first serve basically does the same as round robin without preemption, right? So if I have n processes and q is this quanta, right? You can quantify what that means. You can quantify how that would translate into how much time I wait, right? So basically, I know that if there are n processes, right? Every n minus, after n minus 1 processes, I get to run. So at the most, I would only have to wait for n minus 1 times q time interval, right? So that's a good way for me to quantify how much time I would have to wait. It can probably be smaller than that, because not all processors have to use all their quanta, right? So how I choose this time interval becomes crucial. So if it's too large, it becomes FIFO or first come first serve model, right? If the quanta is too large, then basically everybody gets to run. Whoever came first gets to finish their task. If it's too small, if it's smaller, right, then I get to reduce the wait time, right? In the equation n-1 times q. So if I keep the q small, then it looks like you are getting the CPU a lot often, right? It also means that you don't actually get to do a lot of useful work within that time, but it at least looks like your waiting time is reducing, right? And the smaller you keep it, the more you're going to pay in context switching time. So because now you're going to context switch more often, right? And this is the parameter that you're trying to manipulate for your homework project, right? You're trying to figure out how often the system schedules events, which is the timer, right? So you're trying to change it from a few hertz, 100 hertz to 1000 hertz. 100 hertz is, 100 times a second, which is 10 millisecond, and 1000 hertz is 1 millisecond, right? So you're trying to see what happens when you change this Q, right? And if you reduce the Q, then it'll look like you are moving faster. Unfortunately, for the example that you're looking at, you're only measuring the overhead, right? You're measuring the overhead of the stuff. So depending on what your scheduling is, you will notice different stuff, right? And when you have the kernel running for different intervals, try to see how it feels for interactive use or other parameters, right? And you're free to try to make that number even larger. Make it go to 1 second or something, in which case your machine will look awfully slow because it's behaving like first come, first serve, right? So this is essentially what you're trying to do, and right. So the round robin with a quantum of 20, which means that you get to run for 20 seconds and then you get booted for that particular sequence of arrivals, right? P1 comes in, it runs for 50. So it's irrelevant how much time it needs in the future because we don't really know that, we don't have to calculate that. But it gets to run for 20, then it gets booted out, then the next one, the P2 gets to run, right? It only wanted 17, not 20. So it gets to run to completion, and then it goes out. Then you schedule the next one, and that gets its full 20, and so on, right? So basically, any process which comes in gets to run for 20 time units. If it finishes sooner, good. If it doesn't finish, if it takes all the 20, then it gets preempted, and you put the next one, and you do it in a round robin fashion. So you typically get better response time than shortest job first. Yes?
Is there any time wasted when it switches from P3 to itself?
It shouldn't. So the last one, there's a switch from P3 to P3, right? The dispatcher should notice that nothing is really changing, so it shouldn't do anything, right? Any operating system worth its salt should not do anything there. Yeah.
Do the algorithms sometimes take into account, like, its first process was 21, first time, and it's 20, that it should just run for the other millisecond instead of context switching out? Or?
Since it doesn't know what, so the question is, what happens if you only need like one extra time unit to finish, right? So should I cut you slack? Since it doesn't know, it doesn't keep track of that, no, it can't. In a pure round robin, it can't. You can think of other operating system mechanisms which can have a mixture of round robin with shortest job first and say, you only need a little bit time, so let you run kind of stuff. Again, you have to balance the need for, your desire for complexity to keep the OS simple, right? So typically you don't, and we'll continue the next lecture, some of the multi-level and all those things. So as is, the scheduling in operating systems are fairly complex enough that you don't try with those, right? But that's that. So with that, I'll stop for now, and we can continue with the stuff next lecture.